So we will come here to the problem number 3 of this exercise sheet. So we have here figure 2b shows a loosey power divider for a 50 ohm transmission line system. Again, all electrical lengths may be neglected. So what we have here is I want to use again a power divider, but now I use resistors. So here are the ports. Port 1. This I call port 3 here. This is port 3 and this is port 2. And I assume all over here to have the same resistor. And so the question is, how do you have to choose the value of the resistor for the 3-port to be free of self-reflections? The term free of self-reflections means that, for example, S11, S22 and S33 are 0. And now we go to the point again and say S11 is 0. Of course, it's in principle the input reflection coefficient I write here, RL, I see into this network here. Perhaps I write here as well. We see here RL, the load reflection coefficient, if port 2 and port 3, they must be matched. Again, this means I will terminate here with the characteristic impedance ZC, and in our case this characteristic impedance is 50 ohm. This is ZC. And this should be 0. By definition. And this is the question now is, how do I have to choose the resistor to be that this equation is fulfilled? Of course, if we don't want to have any reflection in the input here, I must see here into this circuit also ZC. I must see the characteristic impedance into this circuit. But now we can, in principle, draw or sketch an equivalent circuit. The equivalent circuit will be now like this. We have here R. Of course, these are all lumped elements here. And then we have the parallel connection of R with ZC. And here we have it a second time. But this is equivalent to the fact that I can say this is R, in series 1 R, and here you have 1/2 R, here we have R, and here we have 1/2 ZC. And if I calculate now Z in here, then you see it will be R plus 1/2 R plus 1/2 ZC, of course, here, 1/2 ZC, and to have no internal self-reflections, of course, this must be equal to ZC. And this is again means that I have 3/2 R will be equal 1/2 of ZC. So this will cancel in principle, and we will find that I have to choose R to be 1/3 ZC. Or if I have a 50 ohm system, then it's 16.6 ohm. So we have to choose R equal to 16.6 ohm, then we will have no reflections here, no self-reflections. Could you follow there, or are there some questions now?
Sorry.
Yeah.
So we just need to only need to look into part 1. Do we need to consider part 2 and part 3 also?
Because of the total symmetry, you see, if I again interchange port 1 and port 3 or so, we have a total symmetry. So if we realize this for port 1, it's also realized for port 2 and port 3. There's because due to the rotational symmetry. Are there further questions? No. Then I come to though the point is now, of course, in the last time we had a look to a lossless power divider, and there we could use the absolute value condition to calculate the transmission factor. But now you see we don't have a lossless 3-port, so in this case we must now find a different way. So there we must in principle come to the definition of, for example, S21 or S13, because they are the same, of course, due to the rotational symmetry again. And we can say S21 would be B1, B2 over A1 if, again, port 2 and I write P2, P3 are matched. So we have the same situation that we must terminate this transmission line with the characteristic impedance, and to realize now the input, perhaps I delete this first here. So, of course, to realize now the incident wave, we must in principle use here a forward traveling voltage. UF, we must apply here a forward traveling voltage, and this forward traveling voltage will result in a A1, which will be equal to the forward traveling wave voltage divided by the square root of ZC, in our case 50 ohm. And due to the fact that I apply here a forward traveling voltage wave, and the point, one very important point here is now that I don't have any reflection at this port, so we must not account for the reflected wave here, but we can say I just apply here a certain voltage UF, and then of course we will have here a transmitted wave amplitude I call UT small t. This is a transmitted wave amplitude, but this would be the wave amplitude sorry, here UT. And then the B1, B2 would be equal to the transmitted voltage also divided by ZC. But you see here, if I insert this into this equation, then ZC, because I always assume to have the same ZC, then this is equal to the transmitted voltage divided by the forward traveling voltage. So they look very much the same, but you see this will be the case. So what we have here, it's in principle a voltage divider. So we will have here also the forward traveling wave amplitude, and here we will in principle have the transmitted wave. UT. This is our transmitted wave amplitude, or I write it here. UT. This is our transmitted wave, and what we do have here is just a voltage divider. So I can now calculate this part. So we can say that the S21 will be equal to UT, the transmitted wave, to the forward voltage. And now we have to account for the voltage divider. Now this is this resistance, it's 1/2 ZC divided by the total resistance, and the total resistance is 3/2 R plus 1/2 ZC. And of course we know from the task before that R, we would have to choose R to be 1/3 ZC, and then you see this will cancel, and we will have S21 will be equal to 1/2 ZC divided by ZC, and this is equal to 1/2. So this will be now the parameter S21, and due to the rotational symmetry we now got the complete S matrix already. So overall S matrix would look like this. We have here a 0, here a 0, and here a 0, then 1/2, 1/2, 1/2, 1/2, 1/2, and 1/2. These are all the same values. This is because of the rotational symmetry. There we have an ideal power divider now, which is, and one of the advantages of the Lucy power divider is that it's essentially frequency independent.